It's turned out that today the globalization has changed a lot of different things, and the volume of air transportation has increased, and also the traffic of goods and people has also increased. And so today it seems that the world has become a super connected small village. So these have different consequences on the human diseases, including the vector-borne diseases. So one of the first consequences is first the expansion of vectors, the mosquito. For example, you have the Asian tiger mosquito, Aedes albopictus. This mosquito is originated from tropical Asia, here in red in this map. And in less than 4 decades, this mosquito has colonized most tropical, subtropical, and even temperate regions such as Europe. Another consequence is the expansion of pathogens, with travelers coming back from regions where these pathogens are endemic. For example, in France, each year, we have hundreds of people coming back with dengue. And these imported cases are located mainly in the south of France, where the mosquito competent for dengue is located, is Aedes albopictus. So the globalization of trade and travels lead to a higher prevalence of infectious diseases. Today, we have more than 25% of the annual deaths worldwide are estimated to be related directly to infectious diseases. And 23% of these emerging infectious diseases are vector-borne diseases. That means 17% of the mortality each year is related to the vector-borne diseases. So, in addition to the globalization of trade and travels, favoring the expansion of vectors and pathogens, a suitable climate is a condition fundamental for the transmission. So insects, as you know, are cold, poikilothermic organisms, very sensitive to the temperature. Here you can see a climatic dendrogram showing the climatic similarities between different regions in the world compared to Shiba. Shiba is in Japan, is the ancestral homeland of the Asian tiger mosquito Aedes albopictus. And these climatic similarities coincide with the geographical distribution of this mosquito, Aedes albopictus. So once introduced, the mosquito should find a suitable climate for its establishment and then expansion. So over the past 3 decades, many vector-borne diseases have emerged in new regions, and many endemic diseases have increased in incidence. So dengue, chikungunya, Zika, and yellow fever are 4 arboviruses transmitted by mosquitoes. Dengue is the most important arboviral disease with around 400 million cases each year, 30,000 deaths. You have chikungunya, which has emerged in the Indian Ocean in 2005. Zika emerged in the Pacific region in 2007. Both have caused several million cases worldwide. And lastly, you have the yellow fever, which is an old disease. But despite of the availability of inefficient vaccine, yellow fever remains a big threat for a lot of countries. So dengue, Zika, and yellow fever are flaviviruses of the Flaviviridae family, and chikungunya is an alphavirus of the Togaridae family. So here you can see that within the genus of flavivirus, we have different clades based on the mode of transmission. You have the mosquito-borne virus, for example, yellow fever virus, the tick-borne virus, here, for example, tick-borne encephalitis virus, and you have also the ISF, the insect-specific virus, such as the self-fusing agent virus. And the ISF branches at the base of the flavivirus genus, suggesting that this flavivirus genus with these arboviruses have an arthropod origin at the beginning. So most arboviruses circulate primarily within a Sylvatic cycle between monkeys as the reservoir host and arboreal canopy-dwelling mosquitoes as vectors in the forested environment. And then the emergence coincides with the capture of a white virus by an anthropozoophilic mosquito, which acts as a bridge vector for transmission of the virus from animals to humans. And then the virus circulates within an epidemic cycle where humans are both reservoir amplification hosts and the anthropophilic mosquitoes, Aedes aegypti, Aedes albopictus, as the main vectors. So dengue, chikungunya, Zika, and yellow fever are transmitted by the same epidemic vectors, Aedes aegypti, Aedes albopictus. Aedes aegypti, Aedes albopictus can also share the same geographical distribution. Here you can see in this map that countries where we have only Aedes aegypti, here in blue, countries where we have only Aedes albopictus, here in red, and countries where they are together, here in beige. So there are more than 3,500 different mosquito species, and less than 15% can bite humans. So morphologically, Aedes aegypti, Aedes albopictus are quite similar. Aedes aegypti is from Africa, Aedes albopictus is from Asia. Aedes aegypti lives in towns mainly and colonize artificial breeding sites such as the flower pots. Aedes albopictus lives in the forest, can also live in town and colonize natural breeding sites such as the tree horse or artificial breeding sites such as the flower pot. The two species have a bite during the daytime, and they also feed on humans. So contrary to Aedes aegypti, Aedes albopictus can also feed on animals. So Aedes aegypti is mainly located in tropical regions. Aedes albopictus is located in the tropical regions, but also in temperate regions, because the eggs of Aedes albopictus can survive to the temperature during winter by entering in diapause. And the two mosquito species can transmit nearly the same arboviruses. So what makes a mosquito competent for human pathogens? So we have different criteria. One criteria is the mosquito should be abundant in high density in a human environment. And also, the mosquito should feed preferentially on humans, so be anthropophilic. And after the infection, the mosquito should survive long enough to be able to transmit the virus by bite. So these three first criteria can be accessed from entomological survey on the field. And the fourth criteria is what we are looking at in the lab, is the vector competence. So you use experimental infections to evaluate whether a mosquito is genetically competent to transmit a given pathogen. So the vector competence and other parameters can be included in the same formula. It gives you the vectorial capacity. And the vectorial capacity is the ability of insect to play the role of vector on the field in the real life. So just very quickly, what is the vector competence? So the vector competence is the ability of an insect to ingest the virus during the blood meal, to ensure the viral replication, and to transmit the virus to a suitable vertebrate host. So the duration between the entry of the virus inside the mosquito, the exit of the virus from the mosquito, is named the extrinsic incubation period. And this parameter is extremely important, as the mosquito female has to survive beyond this period to be able to transmit the virus by bite. So to illustrate these aspects, I will take one example, yellow fever. Yellow fever is a very old disease. However, despite the availability of inefficient vaccine, yellow fever outbreaks are still reported in several places. So yellow fever is a disease endemic to tropical regions of Africa and America. We have 7 lineages, 5 in Africa, 2 in America, and each year were reported 200,000 cases and 30,000 deaths. In 2016, yellow fever emerged in Angola, and imported cases were reported outside Africa, posing the threat of an emergence of yellow fever outside Africa and America. So yellow fever virus is a flavivirus of flavivirid family, like dengue, and the genome consists of a single-stranded linear positive sense RNA molecule. So why yellow fever is so interesting? Because yellow fever illustrates three main steps in the emergence of an arbovirus. The first step is the introduction of a new pathogen in a new environment causing urban outbreaks. The second step is the spillback of the pathogen into the wild, initiating an enzootic cycle. And the third step is the spillover of the pathogen from an enzootic cycle and creating an urban cycle. So let's talk first on the first step, is the introduction. Is the introduction of yellow fever during the slave trade into the New World, causing devastating urban outbreaks. So yellow fever and the vector Aedes aegypti are both originated from Africa. On the left, you can see a phylogenetic tree showing that the yellow fever viruses from South America are closely related to yellow fever from West Africa. So this virus from America derived from the viruses in Africa. On the right, you can see Aedes aegypti. Aedes aegypti, the migratory route of Aedes aegypti, which is an African mosquito, from Africa into the New World. So this is based on population genetic studies. So you can see that this mosquito has been introduced into the New World during the slave trade between the 50th and 90th century. So in the past, yellow fever caused important urban outbreaks in several places in South America, including in some cities like Boston, Philadelphia, or New York. So then, the Cuban medical doctor Carlos Finlay suggested that the yellow fever can be transmitted by the mosquito Aedes aegypti. And then this was later confirmed by the American physician Walter Reed. So this discovery allowed to control yellow fever by eradicating the mosquito Aedes aegypti. And then eradication campaigns were initiated by the Rockefeller Foundation and then by the Pan-American Health Organization. So by eliminating the water containers where the mosquito breed and also the use of the insecticide, the DDT, yellow fever disappeared from South America with the eradication of the mosquito Aedes aegypti. So then, after the eradication of Aedes aegypti, yellow fever disappeared from most cities in South America. So it is our second step with the spillback of yellow fever into the wild in a jungle cycle. So we can say that in Brazil, for example, since 1952, after the eradication of Aedes aegypti, only persists a Sylvatic cycle of yellow fever with the virus circulating between zoophilic mosquitoes, Emergence and Sabetes, and non-human primates. So the urban transmission with the infection of humans by anthropophilic mosquitoes and mainly Aedes aegypti has never been observed again. So we have evaluated the susceptibility of Sylvatic mosquitoes, Emergence and Sabetes, which are very present in high densities in the Tijuca forest, in a forest close to Rio. We have infected these mosquitoes with a yellow fever virus from Brazil and from West Africa. And you can see that these two mosquito species were able to be well infected, to disseminate well the virus beyond the mid-gut barrier in the mosquito, and to transmit the virus at high rates with a high proportion of mosquitoes able to deliver the virus when the mosquito bites. So we can say that Emergence and Sabetes are highly competent to the yellow fever viruses we have tested. So in Brazil, after the eradication of Aedes aegypti in 1952, the mosquito come back again in Brazil after the relaxation of the control measures. And you can see in these two maps that Aedes aegypti is very prevalent today in Brazil. On the other hand, you have Aedes albopictus, the Asian tiger mosquito. And this mosquito was introduced in São Paulo in 1986 and then tend to colonize the southeast region of Brazil, where are located the most populated cities of São Paulo and Rio de Janeiro. So the question is then, can these mosquitoes, Aedes aegypti, Aedes albopictus, contribute to a re-urbanization of yellow fever like in the past? So is our first step with the spillover of the jungle cycle to have an urban cycle. So we have evaluated the vector competence of different populations of Aedes aegypti. Aedes aegypti collected in different regions. Aedes aegypti collected in Manaus, also Aedes albopictus. Manaus, a region which is endemic for yellow fever. Aedes aegypti, Aedes albopictus from Guyana, a transition region for yellow fever. And also Aedes aegypti, Aedes albopictus from Rio, a region free of yellow fever. So we have infected these populations with 2 different viruses of yellow fever from Brazil and 1 from West Africa. And we evaluated 2 weeks after the infection, the transmission by detecting the virus in the mosquito saliva. So you can see that all populations were pretty susceptible to the free viruses. And you can see that mosquitoes, aegypti, albopictus from Rio, are highly susceptible to the free viruses. So another question we had is, can yellow fever become more adapted for a transmission by this unusual vector Aedes albopictus? Just to remind you that Aedes albopictus is a mosquito which can feed on humans and on animals, and then can act as a bridge vector for a transmission of the virus from animals to humans. So then we did passages of the virus on Aedes albopictus from Manaus. I remind you that this is a region endemic for yellow fever, and Aedes albopictus from Rio, a region free of yellow fever. So for that, we have infected the mosquito with infectious blood meal. 21 days after, we collect the saliva from the mosquito, put it on cells to produce the virus, and give it back again to the mosquito. So we did 10 passages. So we evaluate what happens in the saliva of the mosquito. You can see that from the passage 1 to the passage 4, there is no virus which can be detected in the saliva. However, from the passage 5, you can see the virus detected in the saliva of Aedes albopictus from Rio. At the passage 6, we can detect the virus isolated from the saliva of Aedes albopictus from Manaus. So we can say that using our experimental procedure, we were able to select a yellow fever virus more adapted for transmission by unusual vector Aedes albopictus. So we also have a deep sequence, the viral populations at different passages on the Aedes albopictus. So we found in the mosquito saliva two different variants, but two very interesting variants we have found in Manaus mosquitoes, and with a mutation at the position 2772, located in an NS1 gene with a change from an isoleucine to a threonine. A second variant isolated from the Rio mosquitoes and with a point mutation at the position 3303, also in the NS1 gene, and with a change from a serine to an asparagine. And the 2 variants reach the 100% of fixation at the passage 10. So these 2 variants presented a mutation here. So it is known that the intracellular NS1 is central in the viral replication. It is also known that the secreted NS1 can elicit the host human responses. So we hypothesized that the mutation we found in the NS1 gene can alter the properties of our viruses to elicit immune responses, and this should be investigated. So we demonstrated that yellow fever can become adapted for transmission by unusual vector, Aedes albopictus. So this should alert us about the potential of yellow fever to initiate an urban cycle. And to reinforce the statement, Aedes albopictus has been found naturally infected by yellow fever on the field by the team of Pedro Vasconcelos. So indeed, human cases have been reported in a region close to the most populated cities of Rio, in São Paulo and Rio de Janeiro. So in this region, free of yellow fever for more than 70 years. So were reported recently 800 human cases with half death and 4,000 monkeys dead. So this is very alarming. So imported cases of yellow fever are periodically reported outside Africa, posing the threat of the emergence of yellow fever outside Africa and America. So what can be the risk for Europe and for France, where Aedes albopictus is present in 20 European countries and in France in more than 50 French departments. So we have evaluated the vector competence of Aedes albopictus from France for the yellow fever. And you can see that the mosquito is able to transmit the yellow fever from day 14 after the infection with around 50 viral particles detected in the mosquito saliva when the mosquito female bites, which is very, very important. And it's not a very good news. So, in summary, the emergence of an arbovirus can be considered as a process in two main steps. The first step is the introduction and the adaptation of a new vector to a new biotope. We have the example of the Asian tiger mosquito Aedes albopictus. In less than 4 decades, this mosquito has colonized most tropical, subtropical, and even temperate regions. The second step is the introduction and the adaptation of a new virus that can be transmitted by a local vector. I think that other arboviruses can emerge in new regions by becoming more adapted to a transmission by an unusual vector. For example, in Europe, we have Aedes albopictus. So to finish, I would like to acknowledge the people with whom I'm working. So it's mainly the team of the Institut Pasteur International Network. Why? Because we work with field-collected mosquitoes and also viruses collected freshly from patients. And also, I would like also to mention our funding resources, because in addition to yellow fever, we are working with other vectors of different arboviral diseases. And also the members of my team and also my collaborator in Pasteur Paris, in France and abroad. And also, I am very proud of that, we are involved in the teaching of medical entomology, with a course every 2 years in Pasteur Paris, in alternation with a course in the international network. And this year it will be next June in Institut Pasteur of Laos. And we have also a MOOC, so in medical entomology, and it will start next week. So thank you for your attention.
Thanks very much. Are there questions? Yes, please.
Very nice talk, Annabella. I want to ask you about the experiment you did with the 3 populations of mosquitoes from Manaus, Goiânia, and Rio. If they were done with the current circulating yellow fever virus or more old material that were stocked?
The 2 viruses we have tested for these field-collected populations is a 1E and 1D. And so the 1E is the current strain which is circulating in Rio, which tend to replace the 1D. So we have tested the 2.
Yes.
So Annabella, it's very interesting that you show that both aegypti and albopictus are still competent for yellow fever. So why do you think it has not spilled over into the urban cycle yet?
I think that there is attempts to escape from the wild cycle. And what make me very surprised concerning these results, it's concerning Guyana. Guyana, it's a special place which is at the border between the jungle and the more rural regions, and you can see that in this area, the mosquitoes are less competent than the others from Manaus and from Rio. And perhaps at this limit, there is something happening in the mosquito that limit the selection of a variant that can be better transmitted by anthropophilic mosquitoes and from Rio. So I think that is a matter of chance, and perhaps it will happen perhaps soon, because you have different germs outside the forest cycle.
Last question here in front.
Yes, probably a continuation of this question. So you did this experimental evolution of viruses, and you've seen really the hit of NS1 protein. So, and you mentioned that it's known something about immune response in humans. But do we know how this NS1 interacts in mosquitoes? So what allows it to be adapted to this new vector?
I think that the NS1 is well known to the flaviviruses that potentialize the immune responses of the human host for the infection. And at the beginning, the NS1 is more a virulent factor that can make the infection easier in the mammalian host. But perhaps with this mutation in the NS1 gene, they can change the way to trigger the response of the host. And so we have to try with the different clones to try to do some experiments on animals, and the problem is that for the flaviviruses, the animal models are not very good. So we have to work with immune deficient mice, but this is not a very good model for that. So we have to improve our strategy and perhaps do with humanized mouse, which is very costly.
Thanks very much. I think we'll move on to the next speaker. Thank you.